So let's now take a look at some of the properties of a binomial probability experiment. The first property is there needs to be n repeated, independent, and identical trials. Now, what's important here is this n. Here, n is fixed. So I know I'm going to do this 20 times, 18 times, 37 times, whatever it is I'm going to do. I know what n is. N is fixed. This is how many times I'm going to do this thing, whatever this is. It could be flipping a coin. It could be tossing 3 coins. It could be tossing 2 dice playing craps. The number of times I'm going to do it, n is fixed. That's what that is. It's repeated. And every time you repeat it, each event, or each trial, we should call those trials, are in fact independent of each other. So for example, if I flip a coin right now and I get a head, and I tell them to flip a coin again, did knowing what the previous toss was, what the result was, is that going to tell you what's going to come up next? No, it's independent. And the independence I'm going to add here, reasonably independent. If you look hard enough, you can probably find a dependence of some type, or at least rationalize a dependence of some type between all kinds of stuff. It's just, are they reasonably independent? Because ultimately what we're going to do here is say, hey, is this a reasonable thing to do? Is this result a reasonable result to use? There's nothing in stone here. Now the trials need to be identical. And again, I'm going to say reasonably identical. Don't get too crazy with identical. I mean, they need to be reasonably identical. As an example, if I'm flipping a coin, every time I flip this coin, do you think I'm really going to toss it exactly 4 feet in the air or 3 feet? Would one go 3 feet 6 inches, next maybe go 4'1", next one 3.8 feet, that sort of thing. Could it be that the height that I flip a coin actually has some impact on the outcome? Well, it's reasonably identical. I'm flipping a coin every time. The flip may not be 100% total identical, but it's reasonably identical. If you're shooting basketball, if historically somebody's been shooting, say, 75% from the free throw line, and they step to the free throw line, historically, you would think they have about a 75% chance of hitting it. Now, change the game a little bit. Suppose they were down by 1 and someone was fouled at the buzzer, and now they're going to shoot 2. Well, historically, they've been shooting 75%. But how many times in this person's career have they been in that exact situation where now the whole pressure of the game is on them? Well, that may no longer be reasonable, or it may be reasonable because it's the best that we can do. We don't have the information under so much stress, if we can call it that. But the process is reasonably identical. They're going to sit there, they're going to shoot, and that's what they're doing. So again, the point is this a reasonable thing to do? Not is it exactly laser science perfect? Because you're not going to get laser science perfect with real world situations. Okay, next, there are only 2 possible outcomes for each trial. And that's hence the bi in binomial, bi 2. There's 2 things going on here. Now we're going to label one of them a success and the other a failure. And a success is not necessarily a good thing, and a failure is not necessarily a bad thing. A success is simply what you are measuring. Or I'll say looking for. And well, if you're shooting baskets in basketball, then a success is probably going to be they hit it. If you're doing cancer research, a success is probably going to be when they die. Because what you're trying to do is record when they die, or how many people die, and then compare that to, say, other drugs. Well, it's kind of hard to think of a death as a good thing. Well, it's okay because a success is not necessarily a good or bad thing. It's simply what you're recording. If I'm recording deaths, then a death is a success. Then everything else we would call a failure. So the bottom line here is that there can only be two possible things that can happen. And we'll expand on this and look at a few examples. Now, the probability of success remains constant for all trials. And again, I'm going to add to this the idea of reasonably constant. Go back to the basketball situation where they got fouled at the buzzer and they're going to shoot 2 and they're down by 1. Well, if historically they've been shooting 75% successfully from the free throw line, it's probably not 75% right now unless we have a real cool customer. But that 75% is the best we can do. Now think of it this way. They hit the first one. Now it's a tie game. Now the pressure's really big time on. One more shot and you're going to win. Well, that 75 may be the best you can do because that's all the historical information you have. So we consider it to be reasonably constant. There may be some variability there, but it may be reasonably constant. Now, the random variable records a number of successes in n trials. So if I say the probability x equals x, now in English that sounded really weird, but written out that should make perfect sense. It's a probability capital X, the random variable, equals little x. And I would say probability that x equals, let's say, 2. So this is saying the probability that the person hit both baskets. And I'm going to modify that just a teeny bit. What I'm going to add to that is I'm going to be given, say, given pi. Now, pi is the probability of success. And I'm going to make something up here, say 0.75. I'm going to pretend like it's using this scenario. And n equals 2. Now this actually just completely specified everything I need for the binomial distribution. So the x here is the number of successes, how many they hit, with a probability of success of 0.75, and n there's 2 trials. That's what this notation means. You'll see this notation a whole bunch. Now, what's the data type? Well, the data type is nominal. Well, why? That's because you're recording successes and you're recording failures. That's what your data looks like, success or failure, success or failure. It may be hit, miss, hit, 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 miss if you're shooting baskets. It may be zeros and ones, which is a very common way of recording binomial type data, where there's 2 possible outcomes, where 1 will represent whatever it is you're looking for, in other words, a success, and then the 0 is everything else. In other words, here, a failure. So if I was looking for the proportion of males or something in the class, 0 would be a female, 1 would be a male. That's a very common way of coding gender. A 0 would be a disease was not present, 1 would be the disease is present. 0 would be that they're still alive, and 1 means that they died during a particular time period. That sort of a thing. Now, all of these are extremely important because these are the assumptions. All of these collectively are the assumptions for a binomial. Oops, I spelled binomial wrong. There we go. And an assumption is properties, characteristics that must reasonably exist to use the distribution. So every time you're going to use a binomial, you have to address all of these and make sure that it fits your scenario. And I'll work out some examples for that.